Hello, we are AGH Space Systems from AGH University of Krakow, Poland. We would like to present you what we have prepared for this year's European Rover Challenge 2024. Kalman is our rover which is still evolving, allowing for iterative development and replacing entire sub-modules without suspending the rover's operability. Our team consists of students with diverse academic backgrounds, ranging from robotics and computer science to chemistry and geology. We have 4 specialized subteams: mechanics, electronics, software, and science. Each subteam has its own leader, who is responsible for task assignment and organizing teamwork. In addition, we have a student board and a dedicated marketing and logistics team, which are responsible for obtaining funds, communication with the university, and our partners. European Rover Challenge is the most prestigious student robotic competition in Europe. Taking part in a challenge like this is a driving force for our team to push the boundaries and rapidly develop and integrate new ideas. It's also a great opportunity to discuss task approaches and solutions with other teams, meet experts from the space industry, and share our knowledge and experience with everybody interested in space technology.
The rover's drive system is based on a rocker suspension and 4 independently turned and propelled wheels. This allows us to drive sideways, diagonally, and turn in place. The tires were 3D printed and are the result of many tests and iterative experiments. Mechanical design significantly increases effective ground clearance and helps to maintain rover stability on extremely uneven surfaces. The rover manipulator is the result of several years of development. It boasts 6 degrees of freedom, brushless DC motors, and a centralized controller. The manipulator has a spacious working area that allows for sampling, lifting objects to great heights, and performing maintenance tasks. The flexibility of the design means that we can easily swap end effector gloves for different missions or attach tech-specific modules and cameras.
Good serviceability is one of our main design goals. Batteries quickly slide in and out of 3D printed mountings outside the frame. The arm is connected with just 4 screws and 2 cables. All essential PCBs for our rover and its modules are designed with uniform physical dimensions. They slide right into a single 3D printed box. Replacing PCBs for different missions or in case of failure has never been faster. All of this allows us to switch the robot's configuration in under 10 minutes, while staying under the 50 kilos weight limit. The rover has been fitted with an easily accessible red emergency button which physically breaks the connection to the batteries, completely shutting the power off. Communication between the rover and the ground station is ensured by 433 MHz full duplex RF modules, and video feedback is provided by a 5.8 GHz link. We also develop an additional camera module in the gripper which provides high-resolution video source. This has been tested to provide comfortable control over the rover on distances reaching 1 km with minimum video delay.
Recently, we refactored our autonomous navigation system to use ROS2 with the latest versions of packages. The odometry subsystem is based around the unstandard Kalman filter with inputs from 4 IR-based depth cameras, which ensures up to 5 cm accuracy. We use the IR cameras to map the terrain and to generate a slope-sensitive coast map. Fast and robust computer vision algorithms are used to detect and localize aerial attacks. We also use our own package which integrates YOLO object detection with the ROS2 ecosystem. This package allows us to easily train YOLO models for any computer vision tasks in future competitions.
In addition, we developed a custom Unity engine-based simulation, where we can achieve high visual fidelity required to run visual odometry and leverage C# scripting capabilities to quickly and easily implement interactive testing environments. We test the autonomous traversal on a weekly basis in a variety of difficult real-life environments to make sure that our system works irrespective of terrain type or weather and lighting conditions. Over the past year, we have been collecting feedback from operators and refactoring our ground station. We control the rover with an intuitive, custom-made controller that can take advantage of our rover's driving model. The manipulator is controlled with a space mouse supporting inverse kinematics or a standard gamepad. We also have the ability to record and execute predefined trajectories.
We are working on a drilling model, taking and sealing subsurface samples. We manufactured the prototype where we identified the subsystem problems. We consulted our issues with the experts and created a design of the next iteration that eliminates errors, has smaller dimensions, and sufficiently reduced weight. In addition, we will place a small probe on the manipulator. which will allow us to measure soil moisture at the appropriate depth.
The rover's vision systems are crucial for the science part of the challenge. We use a hybrid solution. Analog cameras allow operators to navigate with minimum delay, while offline digital cameras provide high-quality footage we leverage after the traversal. We use proprietary software to quickly extract images of Easter eggs and objects relevant for hypothesis testing after the traversal is done. We also focus heavily on preparing a detailed strategy for the traversal, based on the delivered images of the Mars yacht to ensure the mission goes smoothly. Additionally, report templates allow us to provide results of our findings within the required time limit. Our scientific methodology can be easily adapted, depending on the Mars yacht's announced terrain. Apart from the vision systems, we can use our onboard laboratory modules to conduct chemical experiments. This allows recognition of compounds in source samples, which extended the scope of the hypothesis that we can check.
As geological support, the visible near-infrared reflectance probe with fluorescence mode shall also be included. According to the prepared spectral database, the analytical instrument can determine and identify types of minerals.
Our team is designing a drone that can be operated manually and autonomously and will be used during science droning mission. The software stack will be based on ArduPilot. The drone will be equipped with GNSS receiver, IMU, barometer, and set of cameras. In addition, each year we take part in numerous science fairs to inspire future generations. None of this would be possible without support from our university, Ministry of Education and Science, and private sponsors. Thank you, and see you in space.